Keep it close.
Yep. Good afternoon. My job is to say something about the relevance of Planck in the area of diffuse low-frequency galactic components. As you will all know, there are 4 and perhaps 5 major emission components. They're the synchrotron emission, the free emission, anomalous emission, sometimes called AMI, but so it's the spinning dust emission, then the thermal or vibrational emission from larger dust grains. And then the, as a 5th emission mechanism, perhaps is the mechanism that gives rise to the radio that's associated with the gamma ray bubbles. And I'm going to split my talk into 2. One will deal with the intermediate and higher latitude emission, which includes such regions as the Gould belt system, the spurs that dominate the synchrotron maps, and the haze bubbles, and then to say something about what's happening in the inner galaxy. The emission components that we see are illustrated in the Planck maps, but starting off over here in the true synchrotron at 408 megahertz, you've got this large, oops, this is my problem, sticky finger. You can see, oh bless my heart, my finger is too large. Anyway, I'll stick with this. On the left-hand side, you'll see that the synchrotron has a large number of filaments that come from the plane up to high latitude, and the big obvious one is the North Polar Spur. And you can see it rather more clearly here. And if I go back to this one, these are the Planck maps, and if you follow across from the synchrotron over here, there's some strike. It's a very lively beast. If you come over here, you'll see some of this left at the 30 or the 28.5 gigahertz area, but once you get into the higher frequencies at 70 gigahertz, you've got a pattern here which is very similar to what you get in the high frequency channels, which is basically all dust. And so up here, I'm going to have to control my fingers a bit better than this. Up here at 28, you've also got a mix of free and anomalous emission, about half and half, in fact. And you get into the 70. Oh God, sorry. Into 70, you've got basically free is the major emitter, and dust here on the right-hand side. The full sky emission at 408, as I've said, is filled with these emission components, and here the contrast is such that one is able to see a lot of that fine filamentary structure. See all this stuff coming here, and there's what I call a rectangular area in the center here we'll come back to a little later on. But although I'm calling this a synchrotron map, it has a substantial amount of free. Things like these arcs here are part of the what we call the Gould belt system, which is emission from a region that we'll define a little later, but it's in the south here and in the north here, and it's all muddled up with these other features which we'll come back to. There's a big challenge in front of us at the low frequencies to understand everything in the sky. Now, the synchrotron story has moved ahead with the polarization results that have come from WMAP. And if you then go back to our old 408 map and then compare with what's happening with the polarization, you'll find that the polarization features, although not very obvious in the total emission at 23 gigahertz, show these same filamentary structures as you can dig in and see here. And you dig in by getting rid of the more extended emission here with what we call an unsharp mask, that you smooth the data to about 5 degrees and then subtract the smooth data from the actual data, and you're left with these well-defined features. And you'll find that a lot of those match up with these features in here and sub-features in the sky up here. Now, the other remarkable thing of polarization, and this is where the Planck data are going to be extremely useful, is to actually get a good spectrum for the emission, and knowing that the features here are polarized in a direction such that the magnetic field is running along the outside of the structures. And so you can actually pick up a lot of structures in here that are, although they're relatively weak in total power in polarization, they actually have aligned structures. You find it somewhat difficult to see here, but you can see a lot of these outer, weaker features, like this little fellow up here, are polarized along so that the magnetic fields are along the edges all the way down here, and there's features out here coming up here, and you can have a great game trying to understand them. Now, it's true that not all of those have magnetic fields that are parallel to the edges, and a lot of that is because there's a background polarization on which some of the features sit, and that's the sum of the two polarizations that you see. But the bulk of those elongated features are highly polarized with the direction I was mentioning.
Use that separately. Just put that down.
Oh, yeah, that's better. And I can use that.
Just use that, yeah, exactly. Yeah.
That's better. Yep. Now, we've known about these loops and features in the sky for a long time. As I've said, we can do much better now with the polarization data, and this is where Planck's going to be particularly important. The other thing that we can say about this structure as well is that once you get into the Planck frequencies, even the low frequencies, the Faraday rotation is very small. It's less than a degree between K and Ka. And so you are directly measuring the magnetic field direction with the polarization. You don't have to unwind it with Faraday rotation. The other point I would make, while we've got this picture on the sky here, is to notice this rectangular structure which lies above the inner galactic plane, and we'll be coming back to that a little later. But a number of the features that you see are the well-known ones, but they're turning up in polarization now in a much cleaner way. Now, the features, the major feature that we see is the North Polar Spur. There's this feature up here, and that's now had its distance measured in a number of ways, and it's somewhere between 100 and 200 parsecs. That's very much a foreground feature, quite distinct from the haze, which is probably a galactic scale, and well, we really don't know what the distance of a lot of these other features are, and that's one of the things with much higher sensitivity in the polarization. We may be able to say something from the Planck data. But notice that with this local object, there's a lot of correlation with local features, not surprisingly. If you these are the X-ray pictures, and you see this outer envelope here follows this structure. You come up to a slightly higher energy and you can get nearer the plane, and you find again those structures are similar. Other features there that are the interaction of the supernova with the interstellar medium locally within the Gould Belt system. Then there are the gamma ray and radio haze, the bubbles, which is quite an interesting situation, because here you have gamma rays extending way above the plane, which are not clearly the normal pion decay with matter in those areas. And this has now been sort of widely confirmed with the Planck data, which I'll show in a minute. And it's because the Planck data has got good sensitivity, you can confirm the general story that came out a couple of years ago. And the brightness of the haze, when you scale it, actually has a flat spectrum, which when you correct the individual channels, you can actually see it as a common brightness. And we see this on the next slide. This is what the haze looks like in the Planck paper, and it's clearly a phenomenon that's in both the north and the southern hemisphere. You can see it here, and it covers this general area. And these channels have all been changed in amplitude to make the haze look constant, and you can see running from 23 right through to the Planck and WMAP frequencies. So it's clearly demonstrated across a wide frequency range, and then that's the radio side of it, and the gamma ray side in the south, where it's free from the local Gould Belt stuff. This is what the radio story looks like, and this is the outline of the gamma ray bubble, showing that that's very much connected. What the mechanism for the gamma ray emission and the radio emission is still under some discussion, and more than that, what is it that's responsible for this curious combination? Are they supernovae? There are many theories in the literature. Now, then we have what you might call the total gaseous matter, and although this is not a part of what you'll get from Planck, it is related, as we saw before. These loops in hydrogen, for example, follow the outside of that north polar spur, and you'll see it in the dust absorption. And there's even a suggestion of it in the Fermi data, which is the pion decay type. As well as the pion decay type, there is this apparent gamma ray correlated material in here, but that is very much mixed with the other components. And this is where extra Planck data will be extremely important to look at those intercorrelations. Now I'll just pass on now to the free-free. The free-free, you can have a good template in the H-alpha data, and the H-alpha data itself needs correction before you get to the equivalent of the free-free. You have to know a temperature, you have to know what absorption there is, and how much scattering there is, and then you can get a free-free map. This is the WMAP, MEM map. Now we move on to the AMI, and that's got a characteristic spectrum that you can include in your component separation exercise, and that's the purple plot here, which is distinct from the steep synchrotron, the flatter free, and the thermal dust. And this is where Planck is extremely useful in helping to give us the tale of the dust emission, and the extrapolation there is extremely important in understanding that. And this is what the spectrum, if you can isolate an object, and this is the early Planck paper showing the spectrum of the Perseus molecular dust, and you can see here how well defined the anomalous emission is, and you can see how important it is to actually be able to extrapolate down here to define on the right hand side a good spectrum. So the similar thing there again, you can get a component separation for spinning dust by using the 100 microns, or in our case we could use the higher frequency Planck data, and you can see how the WMAP people have used that, and the spinning dust looks exactly like that, but that's where the prior came in, and so you're seeing the prior rather than an independent assessment. This is what the structure of the Gould belt system looks like. We sit in the middle of that, and all I want to say at the moment is that that's a region of star formation with a goodly number of OB associations. The age is 20-30 million years, and you can work out the number of supernovae that will occur in that time, and that's going to be an important energy input, and that's what we may be seeing partly in those features on the galactic plane, a part of it at least. The inner galaxy, and I want to look for a moment at the region in here, and these inner spiral arms, and this is looking at low latitudes where you can actually see a very narrow distribution. Here's the synchrotron again in this rectangular area that's related to the inner galaxy. You come up to the Planck frequencies, 28.5, 70, and 545. You're going through the region of free, anomalous dust, free, and dust up here. And you've got very narrow components. And then the galactic center area, now just focusing on that. And this is, I think it's the mystery area, and that's one of the big challenges, is to sort out what on earth's going on, how much of this is related to the galactic nucleus, because here the galactic nucleus is there, and you look at these features, there are several of them that look as though they could come out of that nucleus by one route or another, and the polarization enables you to follow those features more clearly. They're not sort of random things in the sky, but you've got to understand that. And the Planck polarization data with higher resolution and more sensitivity combined with the WMAP is going to help us tremendously with that. Well, you can separate the free and the anomalous emission and the synchrotron by using radio recombination lines to give you the free and on the galactic plane, and this is all remarkably narrow, as is the synchrotron. And these are the latitude cuts, an area for which we've got the radio recombination lines, and you can make the separation of synchrotron and free. You can see here that the synchrotron has a couple of components, one quite narrow one slightly broader, which is the one you just saw, and these are all synchrotron type frequencies. And you look at the polarized data, and you can see the galactic plane with the ordered magnetic field is very narrow. It's the same width as that structure here. And the pulsars are again in a narrow regime here, because they are related to the supernovae which give rise to that inner emission. Right, I'm coming to the end now where we'll just run on to see the widths of these various features, and there's a very clear-cut change of width. This is in the inner part of the galaxy, leaving out the central part, which is a bit more complicated. But you can see the OB star widths. These are full width, half power, about 0.8, 0.9, up to 1 degree. All the early high excitation regions of these narrow features. Then you get the cooler dust, and then the synchrotron is substantially broader, and that's partly because we're seeing the expansion of supernova remnants and so on that make up that narrow feature in the centre. Hydrogen down here is quite a lot broader, but that's purely because on the plane you've got self-absorption that would be a lot narrower. Then we can get the longitude distributions, and they're all very similar. And we can include there the work on the various components by doing component separation and plotting. This is where I'm finishing. Plotting the distribution of each of the 4 components. This is the thermal dust. And there's a logarithmic scale that we have here. And this has got 5 degree smoothing, which just repeats what you just saw with the longitude range, but we can also then separate out the thermal dust, the free emission, and the anomalous emission there, these two here, the blue and the green. And down here is the synchrotron. And all this is at 28.5 gigahertz, the Planck lowest frequency. You can see synchrotron at that frequency is way beneath the others. And the bulk of the emission is this free and anomalous emission. So I've covered each of the points that I promised with help of so many other people. Thank you very much.
Time for a couple of quick questions. No questions?
Convinced.
I think there's one up there.
Oh, yes.
Is there any microphones up there? Okay.
Can you establish a correlation between the UV indicator and the anomalous microwave emission?
Only in the sense that the O and B star distribution, just coming back to those latitude distributions in the inner galaxy, the UV will be related to the actual O and B star distribution, and that's that narrow one that's similar to the free emission as well, which is a result of ultraviolet. But
such a tight correlation between the free and then it just
yes,
both counterpart of ultraviolet emission.
yes, I think it's partly chance in a way, because the free is coming from the ionized gas, and the AMI is from these dust particles, but they are sort of stimulated. Their energy just is absorbing the UV photons and spinning them up. So the correlations are there, as you imply in your question, but it's not been quantified. And wait till you hear Clive's talk tomorrow, and he'll tell you what happens in individual regions, some of which are dusty and some of which are clearly H2 regions. So they're not one-to-one correlated by any means, but the distributions are very similar. Question.
Any more questions? Okay, well, let's thank Rod again.